Hello everyone, my name is Natalie Redman. I am the lab manager for Freshwater Institute's Water and Environmental Chemistry lab. I will be presenting on monitoring RAS water quality. In this presentation, I'll be going over what parameters are important to analyze, how to sample, and a few methods that we currently use at the Freshwater Institute. So this slide lists parameters that RAS operators should monitor routinely: pH, temperature, dissolved oxygen, dissolved carbon dioxide or CO2, total alkalinity, nitrate nitrogen, total ammonia nitrogen, nitrite nitrogen, and oxidation reduction potential, or ORP if you're using ozone, are all important for system function as well as fish health. It's essential to analyze these parameters because they are all indicators of system performance. For example, your biofilters need alkalinity in order to convert ammonia to nitrate. And CO2, TAN, and nitrite can be toxic to fish at certain levels. And low DO leads to poor fish performance and could also result in death. It's not listed here, but TSS is also another parameter to consider. Fortunately, unlike a lot of the parameters that you see on this slide, you can see solids in your tank without having to directly measure them. But if concentration gets too high, it could be problematic for your system. So when it comes to actually analyzing all of these parameters, it is important to consider which should be measured directly in the tank or in situ, and which are best measured on the benchtop in the lab. So some parameters require in situ analyses because any period of holding between sampling and analysis can affect sample measurements. Other parameters require benchtop analysis to ensure the most accurate measurements. So these methods may require equipment that is best stationed in a controlled environment, or perhaps reagents that you have to be controlled in a fume hood and require PPE. It's also important to consider quality control and to integrate it into your water quality monitoring program. You'll need to consider routine equipment calibration and proper upkeep, as well as sample replication and standard recovery to ensure accuracy and confidence in your data, as well as proper equipment and method performance. So there are a few things to keep in mind when it comes to your sampling procedures. You always want to sample during normal operation. You don't want to sample directly after sampling events, flushing, feeding, or cleaning events. Oftentimes, these events will cause an increase in solids, which is not representative of the normal operation of your tank. You always want to select a representative area of the tank when collecting samples. We routinely collect from the side box of a tank, which is denoted with the red arrow in the picture there. However, if you don't have a side box, that's no problem. You just want to be sure to collect away from aeration and not too close to your tank wall because you don't want to collect biofilm or feed in your water samples. You also don't want to collect samples or take in situ measurements at the bottom drain of your tank. This is the area where you'll have high solids collection, higher organics, and TAN, as well as lower DO due to degradation of materials. So the main thing to remember when you're trying to put together a sampling procedure is that consistency is key. Consistent measurements make it easier for operators to diagnose problems, assess performance, and troubleshoot. So be sure to create a sampling schedule so that samples are taken at the same time of day on the same day of the week if it's feasible. So this table outlines recommended sampling frequency for a stable RAS. However, it's important to note that conditions are always changing as the fish grow. Therefore, these frequencies will change depending on the system biomass, flushing rate, biofilter condition, and your source water. So pH should be measured at least one time a day. Temperature and dissolved oxygen should be measured continuously with in situ probes. Dissolved CO2 should be measured at least one time per week. ORP should be measured continuously if you are using ozone. The frequency of total alkalinity measurements depends on the type of system you have. So for hard water systems, it should be measured at least one time per week. And for soft water systems, you want to measure at least 3 times per week to ensure that you have sufficient levels of alkalinity for your biofilter performance. tan, nitrite, and nitrate should be measured at least 1 time per week. However, when biofilters are breaking in or fish are added to the system, nitrogen monitoring frequency should be increased. So you'll get the most representative data if you measure pH, ORP, dissolved CO2, DO, and temperature in situ. Off-gassing and temperature changes during transport or holding periods can affect these measurements. Also, the parameters that require continuous measurements, like DO, are most easily measured with mounted process probes that collect data 24/7. But for the parameters that don't necessarily require continuous monitoring, like CO2, those parameters can be measured with handheld probes. So these are a few of the handheld probes that we use at Freshwater Institute. Now, of course, there are more types and brands of probes out there, but these are just the ones that we are the most familiar with. But regardless of the brand of probe that you're using, you always want to check the manufacturer's recommendations for calibration frequency, storage, and maintenance. If you don't take proper care of your probes, then your data will not be accurate, and also the probes will break more frequently or need high-cost repairs. So fortunately, most handheld probes include temperature measurements, so there isn't really a need to purchase an additional temperature probe to collect that data. The Hawk HQ40D meter with the attached rugged pH and luminescent DO probe pictured in the bottom left of the slide is better for field use than the regular probes that Hawk offers. However, they are more expensive. The YSI also offers handheld monitoring equipment. The center picture is the YSI Pro Plus unit, and you can attach either a pH or galvanic DO probe to this unit. OxyGuard also offers a range of handheld equipment. The galvanic DO probe is pictured in the top right of the slide, and the portable CO2 analyzer is pictured in the bottom right. There are some things to consider though when you're using the CO2 analyzer in this handheld fashion. The response time of the OxyGuard CO2 probe is dependent on flow velocity of your tank. So if you're using the CO2 probe in this fashion, I recommend collecting a sample and pouring it into the OxyGuard stirring beaker that's also used for the calibration of the unit. By using the stirring beaker, you'll get a result in 10 minutes, whereas if you are putting the probe directly in the tank and you have low velocity, it can take hours for the CO2 probe to equilibrate and provide an accurate reading. It's also important that all of your probes are handled with care, especially the CO2 probe. You don't want to let it hit against the side of your tank, and you always want to keep the tips of your probes free of any buildup or scratches. So process probes that are mounted in your RAS 24/7 are important and necessary for continuous monitoring. Just like the handheld probes, the process probes require maintenance. So regardless of the brand that you select, you want to be sure to check the manufacturer's recommendation for calibration frequency and upkeep. Process probes are great because they allow RAS operators the ability to monitor tank measurements online 24/7, and they'll log data for you. You can also configure the monitors into your alarm system so that you know when or if DO, temperature, ozone levels, etc. deviate from an acceptable range. And just like the handheld probes, most process probes include temperature measurements, so you don't need an individual probe to measure temperature specifically. So pictured in the top left is the Hawk SC200 control monitor with pH, luminescent DO, and ORP process probes. And then in the bottom right is the OxyGuard Pacific monitor, and you can attach pH, galvanic DO probes, and CO2 probes to this unit. A plus side to this system is that you can monitor and manage multiple probes from different systems from one screen. And just a quick side note, the process CO2 probe is the same as the one used for the handheld configuration. So you just want to be really sure not to let it hit the side of the tank and be sure to keep it clean. But again, that kind of goes for all probes, handheld and process probes. If they're cleaned and cared for properly, then your data will be accurate. So you may have heard me mention two different types of DO probes, luminescent and galvanic. So this table outlines the differences. The Hawk DO probes are luminescent dissolved oxygen probes, or LDO probes. These optical probes utilize a light-based reaction to measure dissolved oxygen concentrations in the water based on quenching of luminescence in the presence of oxygen. The LDOs require that the sensor caps be replaced once the luminescent coating is depleted or damaged, and they do not contain a membrane or fill solution. However, they are less robust than their galvanic counterpart. The galvanic probes, like the OxyGuard and YSI units, rely on a chemistry reaction to measure dissolved oxygen in the water. The oxygen that diffuses across the oxygen permeable membrane produces an electrical current that is directly related to the oxygen concentration. These probes do contain a membrane and fill solution, and they are a bit more robust than the LDO probes. However, it is important that these probes remain free of buildup to ensure accurate readings. So now moving on to benchtop analysis. At Freshwater Institute, we analyze total alkalinity, TAN, nitrite, and nitrate on the benchtop in our water and environmental chemistry lab. There are multi-parameter sondes. I know YSI has one that can measure all of these parameters in the tank. However, we have found that the benchtop analysis offers more control and reliable data. So before selecting a method for testing these parameters, it's important to consider the equipment and the consumables that you'll need. We primarily use Hawk, Fisher, and YSI equipment and consumables, but there is a wide range of options out there. Pictured in the bottom left corner is the Hawk DR6000 spectrophotometer that we have in our lab. Regardless of the type of equipment, you want to be sure to understand and perform the routine upkeep recommended by the manufacturer to ensure quality control and proper functioning, whether that be calibrations or replacement sensors. And then before purchasing any chemical consumables like the reagents and standards that are pictured in the center of the slide, you always want to check the safety data sheet, or SDS. An example of an SDS is on the right side of the slide. These documents list the chemical composition, hazards, and how to properly store and dispose of the chemical. And the SDS will also specify if a fume hood is required, as well as any personal protective equipment like gloves and safety goggles. So first up, we have total alkalinity. We use Hawk method 8203, which is adapted from standard method 2320. This method measures total alkalinity, which includes carbonate and bicarbonate alkalinity. And for this method, you use a digital titrator, which is pictured in the bottom right corner, to titrate sulfuric acid into your sample to either a pH endpoint or a color indication endpoint. We titrate to a pH endpoint because it is less subjective than a color endpoint. In order to do this, though, a pH meter with an attached pH sensor is required. If you elect to use the pH meter, you have to remember to calibrate it before use to ensure accuracy. And this Hawk method outlines specifications for sulfuric acid concentration and sample volume that are dependent on the expected total alkalinity measurements. So you have to read the method in its entirety before beginning. I've also linked to a demonstrative video on our LinkedIn page that goes through each step for this method. So why is total alkalinity so important? Well, heterotrophic bacteria consume 7.05 grams of calcium carbonate for every gram of ammonia nitrogen nitrified. Alkalinity levels less than 100 milligrams per liter can have negative effects on biofilter performance. At Freshwater Institute, we maintain alkalinity between 100 and 200 milligrams per liter to ensure optimal nitrification. Alkalinity is consumed at a greater rate with high feed loading and low flushing conditions in RAS. So we supplement with sodium bicarbonate to maintain concentrations. Something to note is if your facility has soft water, then you'll also need to supplement with sodium bicarb to increase the alkalinity concentration of your system. So this table contains alkalinity data for our incoming water sourced from a spring on site and 3 RAS. The incoming water is high in alkalinity because of the karst geology in our area. The RAS water has lower alkalinity because it is being consumed by the nitrification process in the system biofilter. So I'm going to review two different methods for total ammonium nitrogen, or TAN, analysis. The first is the Hach-Nessler method 8038, which is adapted from standard methods 4500 NH3-C. In this method, the mineral stabilizer complexes hardness in the sample, and then polyvinyl alcohol aids in color formation in reaction of Nessler reagent with ammonia. And then a yellow color is formed, which is proportional to the ammonia concentration. And you can see this in the sample vials in the lower left corner of the screen. And this method is a bit cumbersome because there are 3 different liquid reagents that you have to use. However, it is very cost effective. But something to keep in mind is that the Nessler reagent does contain mercury. So any reactive liquid will have to be properly disposed as hazardous waste. The second method we use in the water and environmental chemistry lab is the Hach TNT salicylate method 10205. In this method, ammonium ions react at a pH of 12.6 with hypochlorite ions and salicylate ions in the presence of sodium nitroprusside as a catalyst to form indophenol blue. This method is a bit more expensive than the Nessler method. However, it's a lot simpler. The only reagent that you need is in the cap of the TNT vial. And I've linked to a video on our LinkedIn page that walks through this method step by step. And there is a photo of the test kit in the bottom right of the screen. Both of these methods do require the use of a spectrophotometer like the DR6000 I had pictured in an earlier slide. The intensity of the color that's produced is proportional to the concentration of TAN. So a darker color indicates a higher TAN concentration. So now for some data interpretation. TAN is a byproduct of fish metabolizing feed, so it is a waste material, but TAN buildup can also occur when harsh chemicals are used to clean the system, which ultimately kill the heterotrophic bacteria in the biofilter that work to convert TAN to nitrate. So you want to maintain RAS TAN levels below 1 milligram per liter. The concentration of toxic unionized form of ammonia increases as the pH increases. So it's important to monitor your pH. You don't want to add too much sodium bicarb when trying to increase alkalinity, because you'll also end up increasing your pH and subsequently increasing the proportion of toxic unionized ammonia. So at a lower pH, most of the ammonia is in the non-toxic ionized form. This table contains TAN data for our incoming water and free RAS during the biofilter startup period and then 2 days later. So initially, the TAN levels are not safe for fish during biofilter startup. They're high because ammonium chloride was added to the system to start up the nitrification process in the biofilter. But then after 2 days of nitrification, with the majority of TAN being converted to nitrite, the TAN levels have decreased quite a bit. We use the diazotization methods for nitrite nitrogen analysis. In these methods, nitrite in the sample reacts with sulfonylic acid to form an intermediate diazonium salt. This then couples with chromatropic acid to produce a pink color complex that's directly proportional to the amount of nitrite present. Currently, Hach offers 2 options for this method: the powder pillows pictured in the bottom left and the TNT vials pictured in the bottom right. The powder pillows are cheaper, however, they're not quite as controlled. Users can have trouble adding all of the reagent to the sample test vials, or the reagent can be faulty if exposed to moisture. But just like the TAN TNT vials, the nitrite TNT vials have the reagent in the cap. And I've linked to a demonstrative video for this method on our LinkedIn page as well. So nitrite levels should be maintained below 1 milligram per liter in hard systems and below 0.1 milligram per liter in soft water systems. The threshold, though, is dependent on other water quality conditions, in particular the presence of chloride available in the water to buffer the toxicity. We almost never see nitrite levels above 0.2 milligrams per liter due to the excellent nitrification provided by our biofilters. Similar to the TAN slide, this table contains nitrite data for our incoming water and 3 RAS during biofilter startup and data from 7 days later. So you can see that the nitrite nitrogen concentrations in our 3 RAS are elevated during the biofilter startup period, but then the nitrite levels are high because the bacteria in the biofilter have converted TAN to nitrite. However, 7 days later, after the biofilter has broken in a bit more and the bacteria have converted the nitrite to nitrate, the levels are safer for fish. So I'll be going over 2 different methods for nitrate nitrogen analysis in the lab, the Hawk TNT method and the ISE nitrate method. In the Hawk nitrate TNT dimethylphenol method 10206, nitrate ions in solutions that contain sulfuric acid and phosphoric acid react with 2,6-dimethylphenol to form 4-nitro-2,6-dimethylphenol. It's also a photometric test where color intensity is an indication of sample concentration. So this method does require the addition of a liquid reagent. However, it is still very simple. And I've linked to a demonstrated video for this method as well. And there is a picture of the test kit in the bottom left of the slide. The ion selective electrode or ISE nitrate method, which is standard method 4500 NO3D, is more cost effective than the TNT. However, it is a bit more time consuming. We use a YSI TrueLab and nitrate ISE sensor for this method, which is pictured in the bottom right of the slide. The YSI TrueLab meter requires calibration before use. The nitrate ISE, the way that it works is it is a selective sensor that develops a potential across a thin inert membrane that holds in place a water immiscible liquid ion exchanger. And then that electrode responds directly to nitrate activity. So nitrate nitrogen is the final product of nitrification. Fortunately, it doesn't really become problematic until concentrations are fairly high. We found that rainbow trout exhibited low-level toxic responses, so increased swimming speed, increased side swimming behavior, things like that, when nitrate reached 80 to 100 milligrams per liter. But we've had other cohorts of trout that did not present these symptoms even above these concentrations. We also found no negative effects of 100 milligram per liter nitrate nitrogen to post-smolt Atlantic salmon, but we do have plans to test higher concentrations to provide more information about the potential upper limit of nitrate. So this data shows that initially the nitrogen was mostly in the form of TAN and nitrite during the biofilter startup, but then was converted to nitrate, which is the reason why the nitrate levels were higher 12 days later. So here's a quick checklist to keep in mind when developing your water quality monitoring program. The first step is to identify your monitoring needs. So what exactly do you need to monitor and how often should you be monitoring it? You want to set up a sampling schedule that's feasible, select your methods and the appropriate equipment and consumables, and then you want to be sure to consider cost, maintenance needs, and the lifetime of expensive equipment before purchasing. So do your research and find out what works for you. And then before purchasing any reagents or consumables, you want to review all of the SDSs that are associated with those reagents and consumables to make sure that you have the proper safety procedures in place. And then lastly, you just follow your methods and interpret your data. So just a quick plug, the Freshwater Institute is active on LinkedIn and Twitter, so please follow us to see project updates, tech tips, the latest open access publications, as well as those water quality analysis videos I linked to throughout the presentation. And that concludes this presentation. So thank you very much for listening in. And if you have any questions, feel free to reach out. My email and phone number are listed on this slide.